Okay, welcome back. Today we're going to be going over a lot of what the various parts of the GUI do and explain some of the graphs and how you can start changing things to run your own custom nerve block simulations. And I'm going to assume that you've read the McIntyre Richardson grill paper from 2002 that explains the MRG model because that's what's going to be running in the background. So it's a little bit of precursory knowledge before watching this. So first off, let's make sure that we can open Neuron correctly. So we can go to our Windows search bar and look for the Neuron GUI app. Then when it's open, we can go to File, and normally I would say set your working directory, but because we've been opening it enough times, we can go to our recent directory and see that path that goes all the way to that models folder. And we've already compiled all the models, so we can actually just use the recent directories and it should automatically load up all your additional mechanisms. From there, then we need to load the Hawk file that'll kick everything off. So we went to File and Load Hawk, and then we can go back up one folder because we were in the models folder. We need to go up one layer to the current simulation to get the cnow_run.hawk, and we can run that and that should load everything up. Okay, so there are a lot of windows here. Some of them have been here, are key to the functionality. Some of them have been added over time. But we'll start with it might be helpful to kind of run some of it so we can look at some of the graphs while they're in action. Okay, so these four graphs here, what we have is the M and H gate of every node. So if you remember, the M and H gate make up the activation and inactivation of our fast sodium channel. And so those values scale from 0 to 1. And you can kind of see, what value every node is at. With the electrode, as you can kind of tell, the electrode is at the center. So it's, and we'll go over how we can look at it. But if you really want to, you can look over at this, it's a choose electrode position. Sometimes the names might be covered up, but that's okay. And you can see the X and Y position. X position 0 meaning it's centered, and the Y position 1000 being in micrometers, so microns, it is 1 millimeter away from the axon. So now you kind of know a little bit about the electrode position, and we know the activation gate and inactivation gate. So these last two are kind of much more, we can kind of see some of the blocking stuff. So we have here, this is similar, but this is the voltage. So kind of like the M and H, it's every node. And you can see the depolarization from the electrode. And so right over that center one is where the electrode is, and you can see it depolarizes at, what is this, probably like -20 millivolts. Where the resting potential, is a bit closer to -80. So you can kind of see that. The other graph we have here is a single, you can kind of tell this is on the scale of voltage because it goes from -80 to 40. This is the last node, just about, I think it's one away from the last node of our entire axon. And so the key is usually on this right side here. We are, index 0 of our model. The left side here, index 0. That's normally we're going to be creating like test action potentials to try and block, which means on this opposite side, which would be, where our index is towards the end of our array of nodes. So we have a lot of nodes, and we are using ax nodes -1, which will put us right at the end. By doing that, since we know that we're going to be creating action potentials on this side towards node 0, we can be looking at, node, normally this will be node 100 in a 101 node model, which is currently what's running. And so if we're looking at this side, that means this voltage plot here over time will tell us whether or not we've been blocked. So if we run this, I think it actually should show a test pulse to kind of explain a little bit of what I'm talking about. And we should see a test pulse show up on the left side, propagating to the right there. And so since we know that the action potential was generated, we can look at this one voltage plot to be able to say, oh, it didn't actually go all the way to the end. So now we've shown block, and now we know what all four of these graphs mean and how we can use them. So we looked a little bit about the electrode position. There's additional stuff to change the shape and number of electrodes for different types of waveforms and other stuff like that. So you can change it to a square wave, and you'll notice the different GUI will change along with it. Most of them are relatively self-explanatory. The only note that's kind of weird in language, at least within the GUI, is going to be the word onset. Now, typically in Block, we refer to onset as these initial action potentials that propagate out. So when we watch when the electrode turns on, because normally we're at rest, when it turns on, looks like, why don't we go back to the sine wave to make sure. Notice how in the square wave, when we turn it on, we're looking for, usually there's something called amplitude, and that was at 1, and then you should always look at the units because they should always be listed. It was 1 nanoamp, so that's not really going to do much. If we go back to the sine wave here, we have amplitude nanoamps, but this is 1 million. So that is going to be 1 milliamp, because nano and then times 10 to the 6th will give us a milli. So if we watch again, what I was referring to is that onset. If you saw right at the beginning, let me run it again. Normally onset is referred to as those 2 spikes that propagated out. But when we're looking at electrode parameters in the model, we are going to refer to that delay at the beginning. So notice when I'm running it, see how it's at rest right now? And I can keep running it until 10 milliseconds here. See how t is equal to 10 milliseconds? That is the same as the essentially delay till we turn the electrode on. So that's just a little idiosyncrasy within the naming nomenclature. The word onset in a lot of these electrode parameters refers to how long it takes to get to a certain, before you turn the electrode on, essentially. Trying to think what other things there are. The DC sine wave allows you to do, it's essentially just DC and then high frequency. So normally you're going to be using sine waves, and then most of these are self-explanatory, whether it's frequency, offset being you're adding a constant value to the sine wave so that it's not the average is not 0, you're changing the average value up or down. So that is kind of the majority of the electrode parameters. You can add 2 electrodes and do things like that. You can add 3, but when you start digging into that, it also might be useful that a lot of these electrodes within the code base have their own little model files. So it might be useful to go through and read some of the code to make sure you can see what's happening in the model. Okay, so we have gone through electrodes. We've gone through positioning. We can change the position. So instance, if we make it really close, we make the electrode, instead of 1 millimeter away, now it's 0.1 millimeter, and we click run, we're going to be much closer, so we should see much more depolarization. Of course, we have to make sure we're using proper amplitudes. So let me put the same amplitude that was in last time. Oh, down one actually. And so now we can see when you get very high. So for instance, we really, because we moved it in a factor of 10, but the you know, the electric field that changes quadratically. So really we've increased our amplitude in some ways by a factor of 100, and that's going to cause errors because those numbers are going to exceed bounds within neuron. So just something to watch out for. So that's the electrode parameters. This save data to file is pretty useful. I progressively added more and more parameters that you can save, but essentially for the most part you kind of just want to save everything and then you can look through the data later. And so the point of this is that basically we're going to click whatever files we want and we need to open the files. Then we are going to run our simulation, which will write the data to the files while it runs. And then when we're done with that, we need to make sure we close the files. So if we enter a file directory, you'll get a pop-up window that says enter a directory path. It should end with you know, /. So let me go to my C drive and create a folder. So if we go to C, and let me just make a new folder for neuron data in all caps. So now I should be able to put in C:// and then whatever the directory is. So maybe you have a more complicated path, you need to enter the whole thing. And make sure you end it with the /. And then we just click accept. And so now you'll notice all of these gates are checked, which is useful. And if we open up our neuron data folder, all of these CSV files have been created. And so that's useful. So now I'm going to run it for just a couple seconds. Why don't we move the electrode back to where it should be at 1,000 microns, so 1 millimeter. And we'll hit run. And so now every time step right now, it is saving to file, which is quite useful. So I'm going to let it run for, I think that's long enough, you know, almost 15 milliseconds. Now, this is very important that you have to remember. Once the data, like the folders are open, every time step will be saved. So if I hit init and run again, it's actually going to continue saving to file. So if you don't remember to close your files, what will happen is you can end up writing tons of data to them and it'll be extremely hard to read through them, and they're going to be giant files. So make sure when you finish running, you know, whatever that one test is, I recommend only doing one simulation while saving. So now all the boxes have been checked, we can close the files. And so now you'll be able to see in the folder the file size should appear. Additionally, if you want to save only a specific couple of these, you can pick one or two and it'll enter a file path it'll want you to put in, and this one you'll have to give the entire CSV file path. So I will accept it, and then when you picked your one, or maybe you want a couple of them, you commit the selection, and that is what will create the file. Then similarly, you run your simulation, and then you have to make sure you close the file. So that's a little bit at how you save data. Later we can go in on how you can look at this data and how you can process it. The next various piece of this big puzzle here, we have the threshold detector. So similarly to changing electrode parameters, sometimes what we're going to want to find is the minimum amplitude of a given electrode setup. So given a frequency, given the delay till it turns on, and given a duration, given a what shape the waveform is, given all that, we're going to want to find the minimum amplitude at which we can block an action potential. So there's a couple things that we have to do within that. First, we have to define the lowest and highest amplitude for the electrode. And so you can make these giant, that won't be a huge hit. It just increases the search space. So it will take a little bit longer the larger the search area is. But you can speed that up by looking at the search resolution value. So maybe you have absolutely no idea. You can make your lower bound 1 and your upper bound 10 million, but make your search resolution 100,000, and that way it'll only automatically run enough trials to get within 100,000, and then from there you can increase the resolution to where you need to. Additionally, there's stuff, so obviously if we're testing if an action potential gets blocked, we need to define some things about the action potential. So first, the AP count detection threshold. This is what's going to be at the end of the axon. So remember, our action potentials start on the left or at index 0, and they propagate to the right or towards the last index. And when it gets to the last index, we need to define what voltage is enough to satisfy there was an action potential. And so normally we can just stick with negative 10 millivolts. To create the action potential, we need to set up a couple things. We need to define the, so this is an injected electrode. So we're injecting current right at the beginning of the axon. And we need to define the delay is when. So we're going to wait 50 milliseconds and then inject current. We're going to define how long we inject current. So we're going to wait 50 milliseconds, and then for 0.1 milliseconds, we are going to inject a certain amount of current, in this case 10 milliamps. And these are pretty standard parameters for that. If you do change one, you have to make sure you update the stimulus value. If I just write 30 here, it's not actually going to update it until you click on it. The rest, the anodic coefficient, you shouldn't need to mess around with. And so essentially all you have to do is click find threshold. And these actually should be appropriate parameters to find a 10 kilohertz. So notice the frequency over here is 10,000, so 10 kilohertz sine wave. We can kind of look around through here, and you'll notice at the bottom is the current lower bound and current upper bound, and the current high frequency alternating current test amplitude. It'll always say high frequency alternating current, so if you end up doing DC or something, it might look a little funny, but it's fine. The key thing we're going to be looking at is actually this background here. So while that runs a little bit more, I can explain just a little bit of this extra UI down here. You'll notice it says efficient search. It will not record number of initial spikes. So what we need to do for every trial here, you'll notice it ran once. It's going to run a second time. And first we need to run a trial with no test pulse to define how many action potentials were generated. Then we run a second trial where we add the test pulse later, and then we can check and make sure that there's one more action potential generated on one side and one less action potential generated on the other compared to just the normal trial. So that means every amplitude we're doing, we're going to require 2 trials. theoretically, if we already knew exactly how many action potentials were going to be happening, we could write that number in, and then we would know. So actually, when I clicked it, it probably actually messed up some of this. So I'm going to stop it and find the threshold again so that we can get a cleaner look at it. And so I'm going to just leave this one alone and let it run while I explain these last little bits. The sine ramp, that's more electrode UI. Same with the sine ramp graph. This, if you do an advanced, some sort of CNOW waveform, something where you're combining DC and ramps and high frequency, you need to be able to see exactly what that waveform looks like, and so you can use this graph here to look at it. So the choose a diameter UI is pretty important for choosing. You need to set this up at the beginning before you start playing around with all your electrodes and stuff. You should pick what diameter you're going to use and stick with it for the remainder of the session that you're doing. So there's everything from the traditional MRG model. In the initial paper, I believe, defines 7.3 to 16, and the 5.7 was added on later. And so when you pick one, it has to essentially recreate our entire axon when you change from one to the next. Similarly, there's a sensory model, and there is a frequency-dependent membrane capacitance that you can add to the MRG. So if you're already using the MRG and you want a frequency-dependent membrane capacitance on top of it, you select this box as well. Right now, there's no way to just remove it. So because sometimes maybe you don't want to have it, or you're trying to compare to previous work that only had the MRG model, that's what's traditionally just open when you start this program. But when you want to start doing new simulations, you likely should include the frequency-dependent membrane capacitance. The last kind of window over here that we'll look at is the mechanisms. You really shouldn't need to mess around with this too much. A lot of this is when we're experimenting with trying to add new parts to the model. So you really should just be able to leave ax node clicked. That is the model that is used for every node in our axon. And so that is, you shouldn't need to mess around with this one too much. So we've been running this for a while. Let's see what our output looks like. So it starts here. It says outputs are given in the order where we have testing amplitude, was a stable state reached, and then we need the count of the proximal spikes, the left side, and we need the count of the time of the proximal spike, and then we need the count of the distal spikes and the last distal spike, and then the count of distal spikes without stimulus. So and then was there block. So the first trial at 700,000 nanoamps, 1, meaning there was a stable state reached. So if you notice, eventually, after a little bit of onset, a stable state is reached. Oh, okay. So it seems to have frozen a little bit. Sometimes we can just hit enter and it'll get running. Stable state meaning right here it is stable. It's no longer just continuous activation. The 4, so that would be the number of proximal spikes with stimulus. So when we added a test pulse, on the left side there were 4 action potentials, and then this number over here is on the right side, there were 3 action potentials. And so notice when there's block, the 1 at the end, we have 1 less action potential on the right. as we did on the left, and you can see the times that those exponentials were. So for instance, in this last trial here, this one that we're at 575,000 nanoamps. We can look at this one. You'll notice there was 5 action potentials on the left, and then there was the same number, 5 action potentials on the right, and without the stimulus, there was only 4. So you can see on the left side is the additional stimulus, the added extra action potential, and it propagated all the way to the right. And you can also see the times at which it arrived on one side compared to the other. So you can see the propagation delay across, and then we noted that it's not blocked. And so every time we do block, we're going to decrease the amplitude. Every time we fail to block, we're going to increase it. And that keeps going until the resolution is met, where we keep going up and down, cutting our search space in half in a binary search algorithm. So the nice part about this is you can kind of copy and paste it into whatever you want, and because it's in a nice CSV format, pretty much everything can take it apart and save it. So in this video, we covered just about everything you can see in the GUI, and how to use it, and how to analyze it. So in the next video, we'll probably start going in depth, maybe with a little bit of the code and understanding more about how some of these things are done. So see you in the next one.